Greetings, everyone that's hanging out in here. Hi, nice to meet you. My name is Nathan Kroc, affiliate faculty in scientific computing, the new data science program that we're launching in the fall. And I direct research at NewSci Labs, which is a machine learning AI R&D company locally here in Tallahassee. We work closely with FSU and a lot of master's students, graduate students, PhD students that we work with. So the point of this talk was to sort of make machine learning more palatable and approachable to the masses. So the whole point is basically to start from certain definitions, and then we're going to go through some examples, and hopefully when everyone leaves, which is just the two of you, you'll have a deep intuition about at least what it is, so that you can then ask the questions about how it works and what you want to do with it, right? So, half of knowledge is knowing where to find it and, knowing which buzzwords to search for, etc. So do either of you guys want to give a stab at defining machine learning? This is a relatively challenging thing to define. So, for example, NVIDIA defines it as its most basic. At its most basic, it is the practice of using algorithms to parse data, learn from it, and then make a determination or prediction about something in the world. Right? So that's nice if you're, a lay person, but it doesn't really tell us what it is as practitioners, as people who want to use it. So then you go to maybe Stanford, and they have a much more succinct definition. Machine learning is the science of getting computers to act without being explicitly programmed. There's some truth to that as well. It's a little nebulous and maybe a bit imprecise, but it communicates some important ideas. University of Washington says, machine learning algorithms can figure out how to perform important tasks by generalizing from examples. So there's a really important keyword there, generalizing, which is a much more, I would argue, more precise academic definition of what we're getting to with machine learning. And then Yoshua Bengio, some of you may be familiar with him. He's one of the, I guess what they call the AI godfathers, one of the people who originally invented AI with Geoffrey Hinton and Yann LeCun, or sort of pioneered its popularity. Machine learning research is part of research on artificial intelligence, seeking to provide knowledge to computers through data, observations, and interacting with the world. That acquired knowledge allows computers to correctly generalize to new settings. All right. So at the end of the day, we have basically three sort of ingredients that everyone is talking about. We have some data, we have a thing that the algorithm or the computer or our technology is trying to accomplish, and then we have the performance or its ability to do this and generalize to more tasks. And if you turn all of this to its most fundamental components, distill it down, it turns out that currently the running academic definition of mathematics, mathematic definition of machine learning is this. So I put this here for sort of two reasons. One is because every once in a while we have very mathematically savvy people who can appreciate this and know it. But two, mostly because this is machine learning at its core. And at the very heart of it, everything in here summarizes exactly what machine learning is. All the complication of reinforcement learning, supervised, unsupervised, classification, regression, convolution, recurrent neural networks, all these little buzzwords can all be reduced to this. So my goal is not to have you understand what this means. My goal is to have you understand intuitively what this means. And then that will give you a confidence internally. It's like, I know what machine learning is at its core, and therefore I can now talk about it with a bit more confidence, and I can ask more intelligent questions about it. All right. So I'm not going to go into what these symbols really mean, but at the simplest level, there's three things. Once again, as I said in the beginning, we have S, which is our data. This is the things we're learning from. H is our ability to do things. If it's a primate or something, they have arms and legs, so they can ambulate and move. But if it's a fish, right, its ability to do things, a fish can't climb. So its capacity to climb is constrained, right? So H is basically the ability to do things. And then L is going to be that performance that we talked about. That's like how well you're doing at certain things. And so what is this saying? Well, machine learning is saying that what you want to do is you want to find the function, or H, this ability to do something that minimizes your loss on the data that you're given, S, right? So it's kind of, I'm saying these in multiple ways, and we're going to keep talking about it throughout the whole talk, but that's what everything boils down to. So let's go to the running sort of most popular academic textbook definition of machine learning now that we built a little intuition. So we're going to take that equation we just saw and put them in words. And it is that a computer program is said to learn from experience E with respect to some class of tasks T and performance measure P if its performance at tasks in T as measured by that performance P improves with more experience. All right, so let's just give some examples to build intuition about what this means. So we have tasks, performance, and experience. So what are tasks? Well, tasks is essentially anything. It's a function that accomplishes something. And these are typically, common examples of these are classification, right? You want to say, is this a picture of a dog or a cat? Transcription, right? I have audio and I'd like to transcribe it into some sort of text, or even translation, right? I have text in one form and I want to get it in another, right? So this is a function. You want to identify anomalies. We're all very grateful to our credit card companies when they tell us that somebody, bought $500 worth of beer in Hoboken, New Jersey, right? And then we've got some sort of synthesis task. This can be image generation, generating new audio, new music, etc. These are just examples of tasks that that machine learning is posed with addressing at some time. So what do we mean by performance measure? This is as I put it here, a difficult thing to choose. It's a common area of research, but basically it is any way for you to quantify your algorithm's ability to succeed at that task. And very curiously, it's nowhere near as obvious as one would think. Just as an example I like to give, somebody used a reinforcement learning algorithm to teach a spider to walk, right? And so they gave it 8 legs and they said, walk and figure out how to walk. And the way that they reinforced or encouraged behavior was to minimize the amount of time that its little feet spent on the ground while it was moving. So what did it learn to do? It learned to actually flip over on its back and walk around on its elbows, right? So that's not even kind of intuitively what we would have thought it would do. So choosing the right performance measure can be very challenging and leads to sort of unforeseen outcomes. And then experiences, of course, data set, feedback, just information in its sort of rawest, most pure form. That is what the experience is. Things that you're ingesting and then reinforcements from actions on the output from your function. All right, so I'm going to go to some just basic intuitive concepts that most of you guys are familiar with, but oftentimes we have a slightly more varying audience in attendance. So interrupt me if this is boring or you understand this. But at the simplest level, the way that I just communicate a function is as an input-output machine, right? You have something that comes in and something that comes out, and think of it like a mixer. And then this has access. This is our task, as we say. And then what we have are these parameters. Okay, so this all makes sense, but what's the key component here? And the key component is this. If we move the parameters in some certain way, we control and influence the way that that function outputs things from the same input, right? And this is what allows us to modify its behavior, right? We want it to do what it did differently. Well, how do we make it do something differently? Well, we modify its parameters. So this conceptualization is really at the heart of machine learning. We have some function, it has parameters, and we want to find the optimal set of parameters that allow it to accomplish whatever task we set out to do. So let's translate this to something we're all familiar with, but may not know much about, and that's neural networks, right? So a neural network is just a function like everything else. It takes some input, picture of a cat with a lime on its head, and then it has some output, which is a probabilistic assignment of what that is. Is it a cat? Is it a lime, or a lime cat, or infinitely many other things? And internally, it has a bunch of parameters. And so neural networks operate on these parameters. They operate on the input with the help of the parameters. The parameters govern basically what it does once it sees certain inputs. And so we want to find the optimal parameters such that it outputs a high probability for cat. So it learns to do what we want it to do. Okay.
I have a question. It's like how to define those functions, how to find those functions.
So 2 questions. You mean how to define or how to find?
Both.
Both. Okay. So the definition of the functions, well, okay. So in machine learning, you don't define a function, you define a function space, right? So you define a set of possible parameters that you can search through. And then the question is, how do you find the optimal function within that function space, or the hypothesis class, as it's called? And And excellently, that's pretty much what we're going to be getting to shortly. So I'm going to be explaining that in just a moment. And if I don't or if it's not clear, interrupt, okay? So what are these? Yeah, so these are, it's based on neurons. Let's not go into the definition of this. Okay, so neural networks are based on neurons. It's an input-output function. You basically accept input from downstream neurons, and then it outputs something further on down at the end there. Now, let's talk briefly about this learning process that Juan just asked about, okay? So we have a function. This is a neural network, and it's going to take some input, for example, a picture of the number 3. So how does a neural network operate on an image? What does that even mean? Well, what that means is that it's going to look at every single pixel of the image. It's going to ingest all the data from every pixel, because an image is just a matrix of numbers. And then it's going to propagate through the neural network. And then what we want it to do is to classify what digit is captured inside of that image. All right, so it should be a number 0 through 9. So for this, what we want to happen is we want to pass in a vector of 784, because we have an image here that's 27 by 27, I think. And we want it to output the number 3, which in other words, it's going to output a 10-dimensional vector of probabilities. And we want 0, 1, 2, and then 4 through 9 to be very low, and then the number 3 to be really high probability, or a high color, or a high intensity of whiteness. So what happens if we pass it through? All the information propagates forward through the network, and initially we get utter trash, of course, right? And why is that? Well, that's because we just initialized the parameters of this neural network randomly. And what's the probability that we're going to randomly guess the optimal set of parameters in this 784 in this really high dimensional space, such that it perfectly predicts, the number 3 every time? Practically 0. Okay, so the question is now, how do we determine the optimal set of parameters to do that? Okay, so what we do is we scold the network. We tell them they did a bad job, and then the network feels shameful, as you can see. And we say, okay, well, what we did here is you said that this image, well, what we wanted is for you to say that this image here is the number 3. This is what we wanted, the input and the output pair. However, what you did was this, right? You gave us something that we didn't want. Right? And so how do we sort of quantify this mathematically? Right? What we're doing is we're saying we have an input-output pair. We want you to take this image 3, and we want you to output this vector of all zeros and then a 1 on 3 as close as possible. Yet you gave us this. So to quantify how far the prediction was from what we want, we have to have a cost function, and then we have to take the derivative of it and see how to improve it over time. So that's where we're getting next. So to just conceptualize what we mean is, if we have this one-dimensional axis here, which is the parameters of the function, right? In this case, it's a single parameter function, W, the vertical axis is going to represent the cost, or rather how badly our algorithm performs at the task given a particular value for the parameter. So as we can see, there's 3 values of this parameter W that do relatively well, sort of locally well, but only one of them would be optimal, which would be at, perhaps -2, depending on the scaling there. All right, so the question is, how do we get to one of these local minima? And where did we start from? Well, we randomly chose some point in this space, and we need to say, how do we get to a local minima in here? And what we do that is just by rolling balls down hills, right? This is essentially optimization theory in a nutshell. So we started somewhere, and then we let gravity do its job, and it brings us to a local minima on this cost surface. And then the particular value of the parameter in this cost surface at this point here is going to be our local optimum. All right, so how do we do that? Well, the first thing we do is we take the derivative at the point. We take a step in the direction of steepest descent, and then we move towards where we want to go. So as an example, we start here, we find the derivative. If the slope is positive, we move left. If the slope is negative, we move right. And we do this back and forth until we find our local minima. And then, so as we said, we imagine sort of a ball rolling down the hill. And this is essentially optimization theory in an animation, right? We can all take multiple courses on this and all the algorithms involved, but at the end of the day, this is what's happening. All right, so the question becomes, this is great conceptually, but how does one calculate the derivative of a neural network? What does that even mean, right? And so that is done using what's called the backpropagation algorithm. So another one of these buzzwords to help build some intuition. So we have the forward pass where the information propagates forward through the network. And then we have this backward pass where we take the derivative of the loss of the cost function with respect to the parameters of the network. And so that tells us, by changing the parameters, how do we change the cost function locally, of course, right? So the derivative is only a local approximation to the function, linearly, locally. So this is the way that we calculate the derivative of the cost function with respect to the parameters of a neural network, right? So that's backpropagation. And so once we have the derivative, we can now take a step on that surface, right? And in real applications, it's not just a simple little one-dimensional curve like that. It's obviously not a two-dimensional curve either, but this helps us build a little bit of intuition. The next step, and this is the actual learning, is you say, given the derivative at this point, I know roughly what the structure looks like, and I'm going to move to a new set of parameter values that improve my performance, right? Ideally. I want to basically get better at doing the task that I was doing. I want to find a new value, a new parameter value that allows me to do the same task I was doing better. And so this whole part of the machine learning process is the optimization part. We have numerous different algorithms, and they all perform, differently than others. They traverse and explore the cost surface and the parameter space differently. And they try and find the set of parameters that minimize the loss, at least locally. All right. So Juan, does this answer it a little bit more?
Yes. And now I came up with another question. It's like, because I saw the picture, usually it's like if it's stuck on the local minimum, but how can they get to the global minimum?
Oh, that's a great question. To answer that question, you will be famous. That is a core problem in optimization theory and machine learning in general, right? And that is that very few algorithms can actually give you, a global guarantee, unless your cost surface is convex, right? Like you have a simple paraboloid or something, in which case you're guaranteed to find the global minima because there's only one, and it's the global one by definition. But most, go ahead.
Oh, sorry. Yeah, please go ahead. Yeah, I think it makes sense.
Yeah, most cost surfaces, at least in the machine learning world, are very, very, very complex. They exist in hundreds, thousands, millions of dimensions in space. They're jagged discontinuities. They jump around. So searching this really high dimensional space and trying to find a global minima is an impractical problem. So what often is the case is we just search, we have to settle for a local minima. So I'm not going to go down this rabbit hole, but interestingly, the thing that actually helps us the most in machine learning currently is stochasticity, right? Because in this space, you have a lot of very just steep caverns where you just jump down and go very far. So when the update rule is stochastic, there's randomness. And so the randomness helps you jump out of local minima and get you to more flat, more global minima that allow you to generalize better on the problem statement.
Okay.
So that's a very interesting part of research, machine learning research, is how to find these really generalizing minima, the minima that allow you to generalize well in the problem. All right, so let's just go through a few examples just to really drive this point home. So how about we have a simple linear regression with one parameter, and we're trying to find the line that fits to these points the best, right? And this is a line with a y-intercept of 0. So we literally have one parameter, w naught. And we just want to find a line that minimizes the error between them. Well, as most of us know, this is a convex problem. There's a well-defined solution, and you can jump to it directly. Actually, it has a closed form solution. But we're going to iteratively walk across the surface to see how it works. So if we start there to the left at negative 0.6 or something, we take the derivative and we take a step in the direction towards the minimum, and you keep moving closer and closer to that global minimum at I don't know, what is it, 1.9 or 1.9 something. And that's the slope that minimizes the squared error between our line and all of the actual points there. All right, so this is machine learning. This is a contrived, trivial example of machine learning, but this is what it looks like. All right, so now now that we have a basic idea, let's add on another parameter. So instead of fixing the y-intercept at 0, let's allow it to vary as well. So now our search space is two-dimensional instead of one-dimensional. And we're now searching along a quadric surface, a paraboloid, if you will, right? And so in this case, this is what's going on. We have on the left is the search space. It's the cost function it's the loss as a function of the parameters b and m, which is your y-intercept and your slope. And then on the right, we see the actual function fitting to the points. And you see as we get closer and closer to that global minima there. And in this case, as you asked, this is a well-defined global minimum. You know it's guaranteed to converge to the global minima. You're able to fit to the lines pretty well. All right, so this keeps going, obviously. And to your question, what happens as things get more and more complex, right? What if we want to fit a polynomial? Suddenly now you have more and more parameters, you know, third, fourth, fifth degree polynomials. You've got 4, 5, and 6 parameters, right? So you have n plus 1 parameters for an nth degree polynomial. And so here's just an example of doing polynomial ridge regression. All right, and so we can't really visualize this cost surface. It's in too high dimensions. But this is the idea of fitting something to some data. So this is the machine learning task of regression, right? You also have classification and, you know, approximating data generating distributions, et cetera. But this one task of regression, I think, animates and visualizes well and helps us build the intuition nicely. All right, so to really drive the point home, I made this nice little iterative animation where we're going to step through each and every individual piece of a machine learning task to see how it works. Okay, so we're going to start here. So as I said before, we have this notion of experience, we have task, and then we have performance. And if you understand those three concepts, you understand machine learning in a nutshell. And you can approach more challenging problems from this perspective. So let's use these three concepts and go through a very specific example at each and every step and see how it works. So to do this, I went all over FSU campus and I surveyed a bunch of people on campus and I asked them 2 or 3 questions, right? So, well, one question. I didn't actually do this experiment. This is going to be a joke, but I'm just setting it up. Okay. So I basically went to everybody and I measured their intelligence, right? So the vertical axis is how smart they are. And then we also measured how attractive they are. So how smart they are and how good looking they are. And then we asked them whether they use an Android phone or an iPhone, right? And so the idea is there some way that we can say, if we know how attractive and good looking someone is, can we infer whether they use an Android or an iPhone? And obviously, this is all the data that I collected across campus. And then clearly, the more good looking and more intelligent you are, the more likely you are to use an Android phone. We all already knew that ahead of time. So the question is, we may know that, okay, but can a machine learning algorithm learn that? Right? So that's what we want to try and understand here. So to do this, we're going to go step by step. And I'm going to solve this problem firstly with just a single layered neural network. It's going to take 2 inputs. It's going to have 2 parameters. And it's going to be a linear regression problem. Okay, so this is the neural network that we're actually going to use to solve this problem. That's exactly what it looks like. One of the nodes is going to be the intelligence of an individual. The other node is going to be their attractiveness, apparently, however that's measured by. And there's going to be a set of parameters, which we're just going to call W1. And then the output of the network is Android or iPhone. Classification problem. So what do we do? How do we learn and what's going on? Well, we have our data, which is this experience, right? And so we have a data set, a collection of tuples, right? Which is intelligence and good looks mapped to a 0 or a 1, which is Android or iPhone. Another parameter of another set of good looks and intelligence mapped to another binary value of 0 or 1, right? And so basically this is a classification problem. And then we randomly initialize our function, right? We talked about that. A neural network is just a function with parameters. And so it's going to do very bad at first, but we're going to see how it learns. So what we do is we randomly initialize it. And this is the partition line, all right? That's actually going to try and separate these 2 classes in this 2-dimensional space. And initially it doesn't do so well, right? Clearly, we just randomly chose some parameters, W1 here. So how does it learn? Well, what we do, and this is this notion of iteratively updating with stochasticity, is we randomly sample 10 points from this data set, right? And you see here, we randomly sample these 10 points. And we ask ourselves, which of these 10 points does it classify correctly and which does it classify incorrectly? And then using that, we put it into a binary cross entropy cost function, take its derivative with respect to the weights, take a step across that surface, and then we learn and we move forward. So let's see this. Is if we ask it which ones it got right and wrong, we see things to the left side of the line, it's classifying as iPhone. And so it got a few of those blue dots right. And then things on the right side of the line, it's classifying as Android phone, right? And so you see on the left, it got those 2 Android points up there, those 2 red wrong. And on the right, it got 1 of the iPhone points wrong. And those are all in red. So blue are right and red are wrong. So what do? Well, we update to W2, right? We take the derivative of the binary cross entropy function. We update, we take a little step on that surface that we saw. And then what happens? Boom, this line updates and changes once again. So we went through a bunch of regression examples before, and now this is a classification example. So I'm sort of giving you another perspective, but in a more detail on another related problem. And so what happens now? We took one step. Well, unsurprisingly, we just keep doing this. So you take another random sample, and how well does it perform now? Well, it only got 1 wrong this time. So what do? Well, we update to W3, and we now have a new value. And then we see how well it did once again, and we update it, and we keep going. And now what I'm going to do is I'm going to just show you all of it animated very quickly, and it's just going to iterate through this process, hundreds and thousands of times. And this is our algorithm trying to learn to classify an individual as an iPhone or an Android user based off of some, irresponsibly superficial criteria, which is designed to humor. And it's not doing very well. I mean, maybe it's doing well. It depends on who you ask. But if you ask me, it doesn't seem to be doing too well along the border of the line there, right? So as it slices this in half, it's got a lot of green, a lot of Android users on the one side that it's classifying as iPhone users. And then in the very circular part of the iPhone users there, it's classifying them as Android users. And so what's going on here, right? Let's see, let's pause for a moment. Can anybody recommend a way to improve this algorithm? What do you think? More specific with the variables. So, what are we thinking there? We're thinking adding some extra information to the problem, perhaps, right? So that actually would probably work. That would be one thing to do. And what that would probably do is actually distribute the points in space differently, right? If you had more variables for each person, then the space of these points would get distributed in a higher dimensional space and maybe be easier to separate them. So that is one solution. Actually, what you said is a really good rule of thumb in machine learning. More data is almost always better. It's pretty much a universal rule in machine learning. Just more data is better. So it turns out that the reason we're not able to do well, use more complicated functions instead of a linear one. Yeah, so that's actually what we're going to try right now. Juan, you nailed it, right? So the problem is that we're trying to partition this data set with a straight line. But if you see, it is not what we call linearly separable. A straight line it is not possible to separate these two data sets with a straight line. It just can't be done. So we need to endow our algorithm, which in this case is just a neural network, our function, with more capacity. So remember earlier on, I talked about H as the sort of the function's ability to do things, right? So I used the silly example of a primate with arms and legs to climb, or a fish to swim, or a bird to fly, right? So they have a constrained capacity to do things, right? So a bird just doesn't climb very easily. The same thing is said here, right? My neural network is constrained to only be able to solve problems that are linearly separable, or more precisely, it can try and solve more difficult problems, but it just doesn't have it is not endowed with the ability to do that, right? So we need a neural network with more capacity. So how do we do that in the neural network world? Well, we add, over here, we add another layer to it. Okay, so notice in the previous slide here, we had just intelligence, looks, and then we just separated it with a binary classification, and we made a guess at it. So here what we're doing is we're adding another hidden layer. So we're going to take the intelligence, the looks, the appearance, and then we're going to pass them through another layer, which transforms the data, and then we're going to try and classify it. So in doing this, we've added more capacity to the network. So now let's animate this and see what happens. And so as we see, it starts off fitting a straight line, but then it slowly starts to learn to bend and wrap around and to classify better. And interestingly, the reason that it takes a long time to learn to bend and wrap around is because there are so few examples that it is being exposed to on that border. Because remember, we're only taking 10 at a time and then having it take a look at them. So what's the probability of those 10 that it's grabbing being along that border that helps bend that line, that helps it learn to bend and shape the line? And it's pretty low. These are insights that actually lead to advances in machine learning, ways to accelerate learning. Right? So you want to find the adversarial examples, as they're called, to sort of help it learn to classify more effectively. All right. So we started off, we're like, all right, what's machine learning? We have experience, we have some tasks, some performance, some experience. We have these things involved. And then we said, okay, we can do regression, classification. We have this notion of a neural network, which is just a function with parameters. We visualize them as little graphs like this, but it's just a function with some parameters. So then we need the cost function. We take the derivative of the cost function with respect to the parameters. We take this update step and we move. Okay. So we have a general intuition about how machine learning works at this point. So what I would like to do is to start going a little bit deeper into maybe some of the more mysterious components of why it works and how it works, right? So just as the brief example, and I find this very interesting. What is this hidden layer that I added doing, right? How is it somehow improving the ability of this algorithm? I said it's adding more capacity, and you can say those words back to me and you'd be correct, but what does that mean? Like, how does that capacity allow it to solve the problem? Okay, so let's just take a peek. So if we go to this example, linear classification, this is just like what we looked at before. We have two classes, blue and red, and we would like to learn to classify them with a straight line. The optimal solution is shown on the right. And just as we saw before, we cannot completely separate these two with a straight line. A little bit of the blue curve dips into the red region, and then the tails of the red curve dip into the blue regions. All right, so it cannot be solved perfectly. So how does adding a new layer like this allow it to solve the problem? Well, what's actually happening here? The key to understanding this, it's very interesting, is to consider what it is that we're visualizing on the right-hand side, okay? On the right-hand side, currently, what is being visualized is the input space X and Y, and then the color of classification all the way on the output, okay? So these two nodes that are in green, this is the space we're visualizing. We're visualizing the XY space. This is the input space. And then we're coloring everything with what the neural network is classifying. Each and every point in this space, it's classifying as belonging to one region or another. Okay, what happens if instead of visualizing the XY space, those two nodes that are in green, we visualize this hidden layer, the hyperbolic tangent transformation? What happens if we do that? Well, this is what we see. So now what we're doing is we basically gotten rid of this XY component. And just as we saw before, we have the input, these two green nodes go into a function f, and we separate them with a straight line. So we're doing a linear separation, but this linear separation is in a new space, right? So what that hidden layer did is it applied what's called a homeomorphism, right? You can take the space of input points and you can stretch them and bend them and fold them and do what you want, but you can never tear them. Right? You can never tear them, and you can never fold it on like a hard crease, or you can wrap them around and morph it. And so all such transformations fall under what we call a homeomorphism, and those are all free game to a neural network. So if it's possible to take this input space and stretch it and move it around such that you can partition it with a straight line, then eventually the neural network has the capacity oftentimes to solve the problem. So that brings up an interesting point, is that what happens when you're challenged with the task that there is no such homeomorphism that can solve it, like this one, for example. So now what we'd like to do is we'd like the neural network to learn to classify the blue region and the red region. So we're going to try and learn some sort of a homeomorphism, something that stretches and transforms the space such that it can separate the two. But notice, remember the rules were that you can never tear or fold the space, right? And that since that's the case, there is no such homeomorphism that allows this problem to be solved. And so this is it trying to figure it out, and it just fails because it can't be done. Yet, this is a pretty trivial problem, and we should be able to solve it. And the answer is that we can solve it. And the trick in this case is to actually, and so this is one of the other questions that people ask with neural networks, and this is going to be the answer. So I'm going to ask the question first, so you see why it's answered. Is that, well, how do we know how many nodes to put in a layer, right? Well, how do we know how many nodes to put in a layer? Well, what does that influence, and why is that variable important? A, it influences the capacity. But as we're seeing, what is the capacity really doing? Well, if we add one more node to this hidden layer, so instead of going from xy to another two-dimensional space, we go from xy to a three-dimensional space, then the problem becomes completely separable. And instead of fitting a straight line, we just slice the space with the plane, like a hyperplane, boom, or it's not even a hyperplane, it's a regular plane through this three-dimensional space, boom. And we're able to separate these problems, separate these two clusters now. All right, so this is the sort of a little bit of a deeper look into what's going on in neural networks. What are the layers doing? What are the number of nodes? What do they influence? All right, so if we go into 3 dimensions, you can just grab the red node, grab the blue ring, and then just separate them in 3D, and then slice it with a plane, and you've now classified things on one side of the plane as red, things on the other side of the plane as blue. Okay, so going into higher dimensions is often a neat trick for solving these types of problems. All right, questions? You want to talk about this at all? Does anyone have anything?
I have one question, and I think you explained this very well. It's kind of make me like realize about this. And I have a question: is the nodes the more the better? It's like x, y, and this first layer. If I have like more nodes than 3.
Interesting question. So there's sort of two. I'm going to summarize this trivially, and then we'll actually talk about examples. So you may have heard of the no free lunch theorem.
No, sorry.
Okay, well, it doesn't apply precisely to your question, but in summary, the message is that there's always a cost, right? So the more nodes, the better. So when you say the word better, someone's going to ask you, what do you mean by better, right? So do you mean the better that it can perform? Well, theoretically, no, because in this simple example, 3 dimensions is sufficient to get 100% accuracy, which means if you add more nodes, you are increasing the computational complexity of your algorithm with no benefit in performance. Does that make sense?
Yeah, I mean the accuracy performance. Yeah, okay, thank you.
Exactly, right? So that's the first thing, is that pragmatically, there is a point with which adding nodes no longer helps you, because you've already solved it with 100%, and as you add more nodes, you're not getting any improved performance, right? Mm-hmm. However, there's another theorem called the universal approximation theorem, which states that simply a single layered neural network with infinite nodes, right? So basically, if you allow it to theoretically have infinite capacity, it can approximate any function. Absolutely any function. Well, there's constraints. I think it has to be continuous or piecewise continuous or something, right? So there's obviously always constraints around theorems. But in practice, that concept communicates to most people that the answer is yes to your question, which is that the universal approximation theorem says that the more nodes you have, the better your network is at approximate, or the better your network can theoretically approximate your or solve your problem. However, in practice, that does not turn out to be the case, and that is because optimization is hard. So as you increase the number of nodes, you start going into higher and higher dimensional spaces, and the cost surface gets more complicated. And while theoretically there does exist a beautiful global minima in this new space that we can find, yes, the universal approximation theorem says it's there, we can find it, it'll solve the problem. It's there if we can find it, and it'll solve the problem. The challenge is, how do we find it, right? So your question's a good one, but it's very loaded, right? So it's like theoretically yes, but practically no. So I think that's kind of the answer. Does that make sense?
Thank you. Yes.
Yeah. Excellent. Okay. So, well, let's go into a few more things. So I wanted to just grab a few examples to sort of show some more sophisticated machine learning and what it's actually doing to make it seem less mysterious. So a really common one that seems very human and somewhat scary is speech to text, right? So how can machines learn to understand speech? And so what I'm going to do is I'm going to show you how speech to text is solved in the paradigm that I just showed you, right? Experience, task, performance, and then we move forward. And if we see it from that perspective, it becomes pretty straightforward. So speech to text is just like everything else. You've got a function, it's got parameters, and you want to find the optimal set of parameters that allow your function to solve some task. So what is the task? Well, the task is, given an audio file, I would like to output a string of text. So you have a huge data set of audio files and associated transcripts that were done manually by humans, right? They listen to it, they transcribe, listen to it and transcribe, or even better, people just reading books, right? That's actually the better way to do it, is people, they'll read a book out loud. So you actually go from the transcripts to audio. And then you have this huge data set of audio and text, and you want to find a function that can do the mapping between the two. So going from audio to text is called speech to text. And then going from text to audio is called, well, text to speech or speech synthesis. And these are both very challenging, cutting edge problems in machine learning that seem mysterious and magical. But as we've seen, it's just a function with input and output. So how is this actually done? Well, the first thing that we do is let's just understand and appreciate for a moment what speech is, at least as far as a computer is concerned. And interestingly, it's actually the same biologically. Our cochlea is basically like a wound up Fourier decomposition algorithm. And so it actually basically like learns the spectrum of the frequencies in audio. But so this is what it looks like on a computer, right? If we visualize it and plot it, it's just this sort of wave. And so all sound is just a bunch of differentials in pressure, propagating the molecules. You have different density of molecules moving through the air as I'm speaking, going into the microphone, being digitized, going through the wire, through the internet, to your computer, and then being reproduced in your speakers. It's really quite fascinating, actually. So how does this continuous idea of pressure changes in the air turn into something on a computer? Well, what happens is it has to sample the audio, right? And so it turns this continuous analog representation of pressure changes into a discrete digital set of numbers. So every audio file that you ever listen to is literally just a collection of numbers. It's a bunch of negative numbers and a bunch of positive numbers. And they look something like this. You have a continuous form, and then you just sample it at a different speed at how close these points are. And then those are the numbers, and that's sound. So there you've got it. This is basically audio in a computer. It's a bunch of numbers. So now that we know what the input looks like, it's just a string of numbers. What does the output look like? Well, the output should look like a classification of text to each and every point, each and every number in that input. And so it looks something like this. So you have along the axis on the bottom is each and every sample point, right? As you're going through this audio file, you have all these little numbers. And so for every one of these numbers, that at that point in time, that number is going to be associated with a particular character, right? And so the objective is that you'd like the algorithm to try and learn which of those points in this string of numbers belong to which characters at which point in time. And so if you simply say the word hello, for example, this is what it would look like. Time in milliseconds is along the horizontal axis. And then the vertical axis is all of the letters, the characters that you're trying to predict. So at any one point in time, you've got a little snippet and you say, this snippet probabilistically belongs to one of these 26 characters. And this is speech to text. And this is how it all works, right? And so you just train this on hours and hours and hours and hours, hundreds of thousands of hours of speech text pairs. And eventually the algorithms learn to reproduce it. This is, what does it say? Affected by pitch, accents, etc. Absolutely, great questions. And it's super challenging. And not only that, but what about what are called out of vocabulary words, right? So yes, it's a matter of pitch and accent, and it depends on what data it was exposed to while training. For example, some of us can't even understand people with weird accents, and we're humans, right? Why? Simply because we haven't been exposed to them enough to have mapped their weird audio stream to our intuition of what these numbers, letters, and words should be, right? So yeah, it just needs to be exposed to all of them. So in some of our machine learning research tasks, we have what are called out of vocabulary words. So strange jargon that only exists in certain domains that it's very difficult to train an algorithm on because there's so few examples of it. Or if you're in a city, there's all kinds of streets with just really weird names, right? And so you're reading off the street address to your phone, and then your phone takes a guess and has no idea what that street address is, unless it's Google, because Google has a really impressive database of all the streets and addresses everywhere, and that's in its speech recognition learning, right? So yeah, this is how this works. So speech to text, it's just like everything we've talked about. The experience is the data set of audio transcript pairs. The function that we're actually solving, in this case, oftentimes it's recurrent neural networks or spatially convolutional networks with attention, or recurrent neural networks with attention. There's a lot of different speech to text algorithms. And then the performance is how well it's doing on that, right? So you have to come up with the different loss functions, and there's a lot of research on which ones work better or worse under certain circumstances. All right. So I just wanted to give one example, and then for anybody who's interested, to go through a few examples to build some more intuition. So for example, if I can pull this up and hop over here. So this is called the Tensorflow Playground. And here you can actually create neural networks that learn to separate different problems. So you can pose problems and then learn in real time what's going on. So let me get that out of the way. So let's, for example, just grab this data set, which as we saw is pretty difficult to solve. And if I go down to 2 neurons, and I need to make sure the activation function is linear. And then the output is just 1 neuron. So it should not be able to solve it. I need only 1 hidden layer. I think it's it. And this should not be able to solve it. And so we run this. And as we saw, it just can't seem to figure out this problem, right? So it's calling one side blue, the other side red, and it just does not have enough capacity to solve this problem. All right, but if we, hidden layers, if we add another node in here and we give it the capacity to do a nonlinear activation function, now it should be able to wrap around and figure it out eventually, right? And so here it's learning in real time, and you can see, the loss function here, the classification space. And so, you can explain with different test data splits. You can add noise to the data. You can change the size of the batches during training. You can have different types of functions, different input parameters, right? So you can take X and Y, you can square their variables to see how all this works. You can operate on different types of problems, like the spiral problem. And it just helps you build intuition about how this stuff works. You can add, regularizers and so on. Another one that's helpful is convolutional neural networks, right? So you can actually see, if you take this image of a cup, it's composed of RGB channels, and as it propagates through the neural network, it visualizes the different features at the different layers of the network. So you can see what it's actually learning when it's trying to solve whatever task it's solving, which in this case is a classification problem. So it sees this input image and it classifies it most probably as espresso, right? So out of lifeboat, ladybug, pizza, etc., it thinks it might be an orange, apparently. Not very probable, but it could be an orange, but it's most likely an espresso. Right, and so you can grab different, images. Here's a koala, and it's going to operate on this in real time. And you see the different features that it's focusing on in the different convolutional layers. And it's pretty sure that this is a koala, and so on. And then another really neat one is this. You can actually draw, I'm going to say classify the number 3. You draw it in here, and then it is pretty sure that the first guess is 3 and the second guess is a 6. Right? And so as you move through here, it actually shows you which portions of the input image the convolutional neural network is looking at when it's making its decisions, going from one layer to the next, right? And then it pools them together in the max pooling, and then it does another pooling, and it does an all-to-all layer, then it does another all-to-all layer, and then it finally classifies the output here. And this was the first example I showed you, right? Where it takes an image and it learns to classify it as the digit 1 through 9. And you can interactively watch this happen. And then you can even try and break it and say, okay, well, what does it think this is? This is the letter A. And it has no idea what an A is because it's never been trained on an A before, right? So the best that it thinks it is a 6, apparently, and then the second guess is a 4, right? So, and this is another thing that I think is important for people to understand when they talk about how AI is scary or how it could take over the world or something like that. You know, AI, as far as it is currently invented and discussed of today, and this is obviously an extremely contrived example, but it's still constrained to the same problem, which is AI can only do what we allow it to do, right? We give it capacity to do things, and this algorithm, no matter where we put it or what we do with it, will never be able to output anything other than digits 0 through 9. It's not going to go outside and play basketball or learn to do our taxes, right? It simply classifies images as digits. And so that's that. So yeah, these are just cool things that you can go and look through and experiment with in your spare time if you want to learn a little bit more. And that about wraps up my talk. So thank you for listening. I hope that helped. And yeah, I know we're about out of time, but if you have any quick questions, I'd be happy to chat about it.
Thank you. It's a very great talk. And I have one question. It's like, how many samples do we need to train before we can let the computer to classify whether it's a 3 or 6?
Very good question. And so that you would need to look a little bit more into what is called generalization theory. But there are a lot of rules of thumb, and ultimately it is a function of the complexity of the problem and the space that you're trying to search through, and the capacity of the algorithm. So just as an example, if you have a very simple problem, but your neural network has a whole lot of capacity, hundreds of thousands of parameters, you're going to need a lot of training examples to tune all of these hyperparameters because your space is really big and you're taking small little steps. So you need a lot of examples. On the flip side, if you have a relatively difficult problem, but your capacity is too limited to solve the problem well, then no matter how many examples you give your algorithm, it just can't solve it, like you saw with a straight line trying to separate the circle with the dot. So unfortunately, there is no silver bullet answer for that. That's part of what they call sort of the machine learning black magic, which is sort of the intuition you build with different problems and different architectures and different data sets. But if you want to learn more about that, look into generalization theory, and they have generalization bounds, and so they can give you a little bit of certainty around that stuff.
Thanks.
Yeah.
And another question is because I saw in your slides, it's I think I only saw one layer. Is that possible to have several layers, and each layer has several nodes? But maybe that sounds very complicated.
No, that's standard. That is how it's done. I think what we have found is that depth is preferable to width in neural networks, unless you go to graph convolutional neural networks, which for some reason we don't know yet why. That is not true. But the intuition is that depth is preferred to width. And that's because, as you saw, it transforms the space. So each layer to the next does a homeomorphic mapping and transformation of the input space. And that turns out to be more powerful and more expressive for solving problems than more nodes. Yeah, my pleasure. Well, thanks for having me. And yeah, if ever there's anything else I can do to help spread the machine learning love in Tallahassee, let me know.